Hello again. So this is related rates, and this is all, there's nothing new here, okay? But I just thought it was worth a repeat, following hopefully a deeper understanding of calculus broadly, but also rates of change. So we've got a hemispherical bubble on the water surface is growing in size. So water bubble radius, that is up there. I think that might be my best drawing yet. Oh, I don't know. I'll leave that up to you to judge. So write down the formula for volume. Oh, okay. So volume is hemisphere, so half 4/3 pi r cubed. So that's 2/3 pi r cubed for a sphere, and then halved, and then differentiate with respect to time. So using the chain rule, right, whatever, 2 pi r squared. Part B, find the rate at which the volume is increasing, so that's the v to t, when r is 6, everything's in millimeters, right? Yeah. If the radius is increasing, so dr dt, at a rate of 3. It's increasing, so it's positive. Okay, so basically I need an equation that links dv to t, dr to t, and I know dv dr. Okay, so remember you can basically just treat these things as fractions. So this is dv to t is dv dr times dr to t. So dv to t is the thing we want, which is good, it's already on the left. Dv dr is 2 pi r squared, and dr to t is 3. R is 6. And so it's actually 6 cubed, so that's 216 pi millimeters per second, millimeters cubed per second, but I'm not going to write that down because it's confusing. Find the rate at which the radius increases. So dr to t is question mark, whoops, when the volume is 18, and the volume is increasing at 90. Okay, so they basically got the opposite. We want dr to t given dv to t. So we could use the same equation, and I should be able to squeeze it in here. So dv to t, I might just avoid writing the equation, but basically I'm just taking this equation again. So I get 90 is dv dr, which is 2 pi r squared, times the thing that I want to know. So the thing that I want to know is 90 divided by 2 pi r squared. Now they haven't given me r, they've given me the volume. So that means I need to go right back here to my volume equation and find r. Okay, so volume is 18. So a little bit of side work here. So 18 is 2/3 pi r cubed, multiplied by 3, divided by 2, and that gives me 27 over pi is r cubed. So r equals 3 over the cube root of pi. So this is 90 divided by 2, or 45, divided by pi times 9 divided by the cube root of pi squared. Sorry, it's getting a bit messy. So the cube root of pi squared is pi to the power of 2/3, right? Come on. So this is 45 divided by 9, which is 5, over pi to the power of 1 minus 2/3 from here. So 5 over the cube root of pi. Okay, so I might do one more, and then I'll leave the other two for you, and maybe we could do them together in a conference or something. So find the volume. Okay, so artist pause plaster Paris in a conical mold. Okay, at a rate, so I'll write that down right now, dv to t is 5. At time t, let the top of the pasta have radius r, that's on the diagram, and the depth be h, where h equals 2r, which isn't on the diagram, so I'll just write it there. Find the volume of the plaster and show that it's the same as a hemisphere with the same radius. Oh, okay. So the volume, it's a cone, so it's 1/3 of the relevant cylinder. So pi r squared times h. H is 2r. Pi r squared times 2r. So that's 2/3 pi r cubed, which is the same as the formula we had above. Find the rate at which the radius is increasing when the depth of the plaster is 10. So we have these. So what we do is we try and link them. So I need to work out what goes here. Well, I need a dv on the top and I need a dr on the bottom. And then I just think, can I get dv dr? Well, I can. I've got this equation which links v and r, so I can differentiate it. Okay, so therefore I get 5 is 2 pi times r squared times the thing I want to know. And it says the depth of the plaster is 10, so h is 10, so r, so 2r is 10, sorry, so r is 5. So therefore, dr dt is 5 over 2 pi times 5 squared. So it's 1 over 10 pi. Whatever per whatever. 1, 2, 3. Okay. I might stop there and I might let you try these last 3 during the first lesson, and then maybe during the second lesson we might have a video conference where I can do them for you if you need me to. Okay, see you later.